Let's look at this one, this polynomial question here. So they called it a function, but they didn't really, it's not really a function. So if it's a function, we need a definition, right? Okay, so is this, so remember we said with polynomials, there's two forms of polynomials, factored form and standard form. Which one do we have here? The standard form is most convenient for y, to find the y-intercept and the end behavior. Okay, so the y-intercept is what's true about the y-intercept on a graph. Y equals 0, right? X equals 0, okay? The y-intercept is a y value, right? Such that x equals 0. All points on the y-axis have an x-coordinate of 0. We're not in the positive territory, we're not in negative territory. On the y-axis, we're at x equals 0. Therefore, that's how you do it algebraically too. If you want to find the y-intercept, you set at x equal to 0. So in this case, we get 0. Okay, because if you plug, so this picture is not the picture of the graph of f. I just sketching a polynomial here to show some intercepts. But for this one, when x is 0, you get y equals 0. Okay, and so while we've got the standard form, let's jump down here. This is the end behavior. End behavior is talking about the ends, right? The ends, the far right end and the far left end. So out here on a graph, x gets really, really big positive. That's the right end, the right end. And then over here, x gets really big negative. That's the left end of the graph, the left end. Okay, and we said that what is going to determine that end behavior? So when x gets really, really big, what happens to this thing? What happens to 3x cubed when x gets really, really big relative to x to the fourth? Yeah, it's like 0, like disappears. So for like, when you think in the billions and the trillions and then a trillion more times than that, these terms with smaller exponents basically look like 0 compared to your what's called leading term with the highest exponent. So that's what we look at when we want to know what's happening way out at the ends for really large values of x. Okay, so when x is a really big positive number, x to the fourth, the only question we're asking, is it a really big positive or a really big negative? Positive. And when x gets really, really big negative, x to the fourth, really big positive or really big negative? Also positive, because you have 4 negatives multiplied together. So an even number of negatives multiplied together will give you a positive. You also have to consider if you have a negative coefficient in front. So not only is the even or odd power important, but then if you have a negative coefficient. So if this was negative x to the fourth, then we do the same analysis, but in the end, we multiply by a negative number. So then we would have gotten negative for both of these. Okay? So you have to consider not only the degree, whether it's even or odd, but then you have to also consider if you have a positive or negative coefficient out in front. Okay, so now the x-intercepts. So by looking at the standard form, you can't really see the x-intercepts. Okay, so what do we then in order to do the x-intercepts, we look at what we call the factored form. So the factored form is what you get when you factor the standard form. So this is advanced, your algebra background, you all have done factoring before, so we got to factor this. When we factor this, we get the same function, just in a different form. So what do we start? We're going to first get out all the x's that we can, which is x squared. That's going to leave x squared plus 3x minus 28. And then we keep going as long as we can keep factoring it. Does this one continue to factor? Plus 3x minus 28. So can we multiply two numbers to get negative 28 and add them to get positive 3? 7 and 4 plus or minus 7? Plus 7 and minus 4. So this is the exact same rule as the original rule. It's just a different form. It gives the exact same output values for the input values. But then the advantage to this is factored form reveals x-intercepts or roots. And so any x that makes any one of those factors 0 will make the whole function 0. That's what a root is, or an x-intercept. We're looking for values of x that make y equal 0. So we start here. What value of x makes y equal 0? 0. Next factor. If that factor is 0, then the whole thing is 0, because they're all multiplied, right? And then if this thing is 0, the whole thing is 0. 4. Okay. Questions on this example from the web work? Okay. So a particular type of polynomial functions are called quadratic functions. A little bigger. Thanks. Okay, so we've got an archer. So this right here is an example of a quadratic polynomial function. And that's degree, it means it's a polynomial with degree 2. Meaning the leading term, the highest power is 2 in the polynomial. And this type of polynomial shows up in lots of real-world applications, especially projectiles, things that are flying through the air. If you're measuring some distance, some vertical distance or height above the ground and time, that has those two quantities have a quadratic relationship, or this degree 2 polynomial can model that relationship. So here we have a situation: an archer shoots an arrow straight up into the air, and then he runs for cover, and the arrow leaves his bow at a height of 5.5 feet above the ground at a speed of 240 feet per second. The height of the arrow after x seconds is given by this function right here. An eagle snatches the arrow when it is 385 feet above the ground on its way down. So I'm actually going to put, so question 0 first. Question 0, identify the specific meanings of the input and output variables in this context, and then how are the input and output each represented in the function definition? This is the function definition right here. H of x equals negative 16.1x squared plus 240x plus 5.5. Okay, so that's question 0. And then you're going to graph the function on the appropriate domain. This is for your graphing calculator. So when we do, for our purposes, when we're working on these quadratic polynomial functions, these are going to be graphing calculator problems. You're going to be using your graphing calculator to find values, to interpret the situation. So get out your graphing calculator to answer these. But that doesn't let you off the hook for understanding what's going on. All right, being able to use your calculator appropriately means you understand the quantities involved, you understand what numbers mean, and so these questions will test that. So these questions are a combination of interpreting the graph as a quadratic function, and then there's also review in there too, things we've done before that's important for our exam coming up this Friday and Monday. Okay, so this is a really good exercise. So I'll take attendance, and you got lots of work to do there. I'll just do this first 5. But make sure you answer question 0. So none of the rest makes sense if you're not confident about your response to question 0. So make sure you check that with those around you and make sure you're on the same page. Without having 0 in place, you'd be flailing on the rest. Okay? So you can work together. LP will walk around and help you if you've got a question. But take a good chunk of time here, 10 minutes, 10, 15 minutes, to really think about these important questions.
No, I figured out the maximum by asking for how long after the last one. So like how would you
Okay, I'll interrupt you just a moment. We'll talk and I'll let you work some more. Question 0, like I said, really important. So let's do that. What's the specific meaning of the input? Specific meaning of the input.
The time in seconds since the arrow was shot.
She wants the time in seconds since the arrow was shot.
Yep.
Is that the input? Okay, and how is it represented in the, how is that represented in our function definition?
X.
X. Okay, what is somebody else? What is the output? What is the output? Did you get it? What's your name again?
Joey.
Was it?
Joey or Jason.
Oh, Joey. Okay, so Joey, did you get this? What is the output in this? Height and feet of the arrow. Okay, height and feet of the arrow. And how do we see that? How is that represented in the function definition? H of x is, he said, the time or the height in feet of the arrow above the ground, right? So it's gonna, that's the height above the ground. Okay. Gotta have that to make sense of the rest of this. Now, so then the question comes, how do I get a good window on my calculator to show the graph, show the right part of the graph that I want? All I see is a vertical line, or I don't see anything at all. Okay, it goes back to this. It goes back to what are appropriate or what values make sense in this situation for your input and output variables. Okay, so you just have to think. So x is time in seconds since the arrow was shot. So on our, so you think about the window on your screen. Do you want it to show, say from, so here's your window on your screen. You think about this. So of course we want to start at 0. So on your screen you want 0 to be over here. So the question is, what makes sense for like the maximum time value? Should it be 1 second? 10 seconds, 100 seconds, 50 seconds. So you just want it, 1,000 seconds. So you can start off with a reasonable guess and then adjust. So what's a reasonable guess if we're shooting an arrow at a fast speed up, okay, from 5.5 feet above the ground? Which of these might be reasonable to think that we want to see the whole journey of this arrow? 1, 10, 50, 100, 1,000 seconds. Okay, so maybe 50. That sounds like a lot, but I mean, it's a starting point, okay? Not 1,000. 1,000 is like several minutes, right? It's not going to take several minutes for the arrow to get back down. Not 1. After 1 second, it'll still be on its way up at a high speed. So maybe 10, but that might not be enough. 10 or 50, so start with 50. So again, see, we're answering this question about the window frame by making sense of the situation. What numbers make sense? Okay, what about height? So we're going to start at a height of 5.5, so probably we start at 0. And then what makes sense? 10 feet, 50 feet, 100 feet, 500 feet, 1,000 feet. So think about it and just make a guess. It doesn't have to be perfect on the first try. So you make a decent guess, see what comes up, and then change it to make it better. So maybe start with 500 feet. But if you do 500 feet, you'll see that it's not showing everything. What do? Make it bigger. But don't make it, don't make it 100,000 feet. Make it twice as big or 3 times as big. And so again, you're making sense of these quantities, these variables and numbers that are reasonable in the context in order to find the right window frame. Does it make sense? That's a question that I get a lot, okay? So it goes back to the situation and what makes sense. for ranges of these values. Okay, I'll let you get back to work. And as you're working, you're keeping in mind what your variables are. X is the time since the arrow was shot. H of x is the height in feet of the arrow above the ground. First easy ones. Okay, so what does the point? Yeah. We'll get to that one. We'll get to that in a sec. All right, so number 1, 4, 707.9, what does that point mean? And if we've got the input and output variables down under our belt, then this should be no problem. So what, yes ma'am?
After 4 seconds, the height of the arrow is 707.9 feet.
Well said. After 4 seconds, after shooting the arrow, the height of the arrow is 707.9 feet. That's what that 1 point represents. So this whole graph is just a bunch of points like that. It's just a bunch of, coordinated pairs of the values of a time in seconds and a corresponding height in feet. That's what makes up this graph, is all those points. All those points. Okay, highest point attained by the arrow. So you have to be able to use your graphing calculator somehow to get this ordered pair. And I get 7.423. 45. Why isn't it not? Turn that. Seven point 453. And 899.9. Okay, so the highest point attained by the arrow, the highest height attained by the arrow is? That's our output, right? Our output is height, 899.9 feet. The time at which that occurs is 7.453 seconds after the arrow was shot. Okay, so on your calculator, you need to know how to use either the max function or use the table or trace and find this highest point on the graph and then know what those two variables mean. Know what your x-coordinate means and your y-coordinate means. Okay, in the context. Questions on 1 or 2? Okay, here's an important question because you really had to make sense of the question. So that, what was that? Let me write that down again. That was 7.453, 899. And so how are we going to find when the eagle snatches the arrow? What information do we have? 385. What is that? Input or output? Height. So it's a value of h of x, right? That's an h of x value. So it's going to be a y value on the graph. So a helpful technique for this is to graph the line, y equals 385, along with your other graph. So now you could use the intersect button on your calculator. And when you do the intersect, I get the point 13.109. Or we'll just do 13.1. And 385. So now we've got to read the question carefully. How long after reaching the highest point does the eagle snatch the arrow? 13.1 seconds? No, you have to read carefully. How long after reaching the highest point does the eagle snatch the arrow? So it's the time change from when to when. Yeah, so we want, this is asking for a change in time, right? This is asking for a change in time starting at when it starts to fall, which is at 7.453 seconds for x, to when the eagle snatches it, which is at 13.1 seconds for x. Okay, so this is a change in x, or delta x. And to calculate the change in x, we do final value of the quantity minus initial. And what do we get? 5 point what? 66? If I remember correctly. Is that right? So the change in time from when it starts to fall from its highest point to when the eagle snatches it is 5.66 seconds. So from here, when it starts to fall, to here. Delta x. That's what the question is asking for. That change in time, 5.66 seconds. Anybody have a question on that? Okay, so now this question, how do we do on this? Write an expression with function notation for the average rate of change of height starting at 0.5 seconds for the time period lasting 3.1 seconds. Caroline, did you get this? Tell me. H of 3.1 plus 0.5. Okay, so the general, just the general form of average rate of change is, you have output and input variables. The general form for average rate of change is, what is this in general calculating? Change in y, or change in output, right? The change in y or the change in output, and then average rate of change is divided by change of x, or change of input. Remember that. So she's doing, so why isn't it not, shouldn't it just be h of 3.1 minus h of 0.5? No, why not? Starting. Right, exactly. I got you worried there for a second. So yeah, you're starting at 0.5 seconds, and then if the time lasts 3.1, then the final time is not 3.1, but the final time is 3.6. So h of 3.6 minus h of 0.5 over the change in time, which is you can just write 3.1. Okay, so that's an expression for the average rate of change, the change in height over this given change in time of 3.1. And then when you do then the function definition can give you these values. H of 3.6, you find that using the function definition, minus h of 0.5 using the function definition, then you do the math. So we can check our answers. What do we get? Nice and loud.
What was it again? Change in height? What?
Change in output or change in input. That's the average rate of change. In this case, it's average speed, right? Because height and time would give the average rate of change for, if it's a height and time variable, would give average speed. This is the average speed. Nice and loud. Somebody else get that? Pretty close to 174 feet per second is the average speed over this time interval. Okay. Questions on average rate of change? Question. All right, next. When would the arrow have hit the ground if the eagle was not around? So that is a height of what?
0.
Height of 0, or that's your x-intercept, or your root. So know how to do that in your calculator. Know how to figure that out on your calculator. X equals 14.94 seconds or feet? Okay, remember x is our time since launch. Time since launching the arrow. So x is 14.94 seconds is how long it would have taken to reach a height of 0? Questions on 1 through 5. These are all important questions. You can, make sense of the quantities, use your graphing calculator to answer questions like this. You know about average rate of change. Okay, so number 6, we'll do this fast. For equal increments of time. I'll do 1 second. So in each second, what happens to the height initially here? In each second, what happens to the height? Increases. It increases. Of course it increases, right? He shot the arrow up. So for each second, the height increases. What about the changes in height? The changes in height are shown by these vertical arrows here. With each successive second that goes by, the changes are decreasing. They're getting shorter, less positive. The changes are getting less positive. Those are decreasing changes. Therefore, the rate of change is? The rate of change is decreasing. It's always doing the same thing that the changes are doing. That's why we analyze the changes, because it tells us what the rate of change is doing. The rate of change is decreasing because the changes are decreasing or getting less positive.
Is it also decreasing because it curved down?
Yep, concave down, right? Concave down, exactly. Okay, and then we come to the part where the arrow is descending. In each second when the arrow is descending, the height is doing what?
Decreasing.
Decreasing. The height is decreasing. Here's an important question. Don't tune out. The changes in height, these changes, these vertical arrows, are those changes in height increasing or decreasing? In or D? Are they negative or positive changes? Negative changes. Are they getting more negative or less negative? Getting more negative. Numbers that get more negative are in or decreasing? Decreasing. These are decreasing changes. So the rate of change is? Decreasing. So the rate of change is always decreasing for this arrow. And so that's why the graph is always concave down. It will work now. Yeah, you bet. Yeah.
I sent you the email yesterday.
Oh, yeah.
Yeah, they said they usually shouldn't respond with email because I'm stupid. So if not, you can just fill this out.
Sure.